So, think about a beautifully designed, like, really minimalist terracotta pot sitting on a perfectly curated windowsill. Just picture that for a second.
Okay, yeah, I've got it.
Right. So now, I want you to mentally place that exact image right next to a multi-million-dollar legacy software system, like the back-end code running a major bank.
Wow. Okay. Those are two very different things.
Exactly. I mean, on the surface, they have absolutely nothing in common. But today, we are going to explain why both of those structures actually fail for the exact same microscopic reason.
Which is, spoiler alert, that they trap the waste.
Right, they trap the waste. So welcome to the deep dive. Today we're exploring this really wild synthesis of system design, and honestly, the raw material we're working with today is just astonishing in its variety.
Yeah, it really is. It's all over the place.
We are talking about the hyper-specific biology of breeding citrid fish, the cultivation of microclimates and home gardening, the abstract mathematics of Haskell programming, and even the routing of Wi-Fi 7 network traffic.
It reads like the ultimate manual for someone trying to just perfectly control every conceivable environment. I mean, jumping seamlessly from the biological straight to the digital.
Which is really the core mission of our deep dive today. We aren't just going to catalog a bunch of different hobbies and technical disciplines. We are going to extract the universal principles of system design and optimization that are sort of hidden inside all of them.
Because fundamentally, whether you're coding a functional application or just trying to convince a houseplant to grow, the rules for building a functional environment are basically identical.
Exactly. And we're going to start unpacking those rules by looking at the incredibly unglamorous reality of a fish tank.
Yes. Specifically, the really rigorous environmental control required to induce breeding among multiple pairs of cichlids.
Right, so let's set the stage here. To get these specific fish to breed, you have to create a highly tailored environment. You need to provide mating grounds, and crucially, you need to provide really secure hiding spots.
Right, essentially artificial caves where the fish feel safe enough to lay their eggs.
Yeah. Now, if you walk into any standard pet store, the industry heavily pushes these commercial cement caves or those really beautiful, natural-looking terracotta pots.
Which look great. They sell you this whole visual fantasy of a pristine, natural riverbed.
But introducing those exact materials into a closed biological system is basically an architectural trap, isn't it?
Oh, absolutely. It's a massive trap because cement and terracotta are highly porous materials. If you look at them under a microscope, they are essentially just rigid sponges.
Right.
And in an aquarium, your absolute biggest enemy is organic waste. So uneaten food, fish excrement, decaying plant matter. When all that waste breaks down, it produces ammonia.
Which is just highly toxic to the fish.
Incredibly toxic.
And those porous terracotta walls just become a magnet for it.
Exactly. They trap the organic waste and like aggressive algae deep within all those microscopic holes. You physically cannot scrub a terracotta pot completely clean without pulling it completely out of the tank and boiling it or bleaching it.
Which utterly destroys the delicate biological balance you're trying to maintain in the first place.
Right. So the aesthetic choice you made actively fights against the health of the system itself.
So to solve this, the highly functional substitute recommended for serious breeders is large, aesthetically unpleasing, three-way plastic PVC pipes.
Yeah, just industrial plumbing supplies.
Right. It is a total rejection of form in favor of just pure utility. To me, those terracotta caves are like designer activewear. Like, it looks phenomenal sitting on the shelf. The color coordination is perfect for your Instagram feed.
Sure.
But the moment you actually put it to use, the moment you sweat in it, or in this case, put it into a living biological system, it just becomes entirely impractical.
Yeah, the fabric doesn't breathe, it stains, and you end up wishing you were just wearing an ugly old cotton t-shirt.
Exactly. The three-way plastic pipe is that ugly old t-shirt. Is it visually jarring? Yes. Does it look like a natural riverbed? Absolutely not.
But if you look at the actual physics of it, it provides a completely smooth surface, a quick wipe with a sponge, and the organic waste is just entirely gone.
Right. There's zero friction and maintenance.
None. And yet, it still fulfills the three essential structural functions required by the system. It provides physical decoration to break up sightlines, it offers secure hiding spots with multiple escape routes, and it still provides enough surface area for beneficial bacteria to anchor onto.
Okay. I hear the logic, but I have to push back on this a little bit.
Sure, go for it.
Because the entire stated goal of the setup is to mimic nature, right? To trick the fish into breeding. Humans are psychological creatures, and if my workspace looks like a sterile plastic tube, my productivity completely tanks.
Yeah, that makes sense for a human.
So Doesn't introducing a highly unnatural, perfectly geometric plastic pipe just completely disrupt the biological simulation for the fish? I mean, if I'm a fish, I know a piece of PVC isn't a rock.
Well, that assumption actually reveals our deeply ingrained human bias toward aesthetics.
Really? How so?
We assume mimicking nature means making an environment look like nature to the mammalian eye. But the biology of a fish, or a plant for that matter, doesn't care about visual authenticity at all. Biology cares about triggers.
Triggers, like
Yes,
structural
it's
triggers.
mostly. And this bridges us perfectly into the botanical data we're looking at today. Mimicking nature is entirely about replicating the environmental variables that force a specific biological response.
Okay, so give me an example of that for the fish.
So for the cichlids, the trigger for breeding is often the simulation of the rainy season, like a monsoon.
Right.
So you drop the water temperature slightly and you increase the water flow. You manipulate the trigger. The fish don't need to actually see rain clouds overhead. They just need to feel the barometric and temperature shift.
Oh, wow. Which perfectly explains the mechanics of what gardeners call preventing leggy seedlings.
Yes, that is the exact same principle.
So for those who haven't started a vegetable garden from seed, a leggy seedling is what happens when a baby plant stretches itself incredibly thin, and it grows this really long, fragile, pale stem.
Yeah, they just look super weak.
Right, and it happens because the plant is desperately reaching for a light source that is too far away. The plant doesn't know it's sitting in a cheap plastic tray on some suburban windowsill.
It has no concept of a windowsill.
Exactly. It only knows its biological trigger, which is basically light is weak, expend all energy to stretch upward.
The environmental input is inadequate, so the biological output is compromised.
Right.
If you want a strong, thick, healthy plant stem, you don't need to build a visually perfect replica of a sun-drenched meadow in your living room. You just move the artificial grow light 2 inches above the leaves. The light intensity is the trigger.
Which brings us to bottom watering, which is another just a brilliant example of this principle in action.
Oh, bottom watering is fascinating.
Yeah. Usually when we water houseplants, we pour water over the top of the soil because, well, it looks natural. It mimics rain.
Right, it's what we expect watering to look like.
But bottom watering involves placing the plant's pot into a deep tray of water and then letting the soil absorb the moisture upward through the drainage holes.
Through capillary action.
Exactly.
Yeah.
And honestly, it looks completely unnatural. Water doesn't flow up in nature.
But consider the mechanics of what bottom watering actually achieves. When you water from the top, the plant roots tend to stay really shallow because that's where the moisture sits.
And then that damp surface soil just becomes a massive breeding ground for mold and fungus gnats.
Exactly. But when you bottom water, the capillary action draws the moisture deep into the lower half of the pot.
Right.
That structural trigger forces the plant's roots to grow downward, chasing the water, establishing a much stronger, deeper foundation. And it keeps the top layer of soil bone dry, completely eliminating the mold.
It is basically the three-way plastic pipe of gardening.
It really is.
You're designing the environment purely for the desired outcome and just stripping away all the visual fluff of mimicking rain, which really makes you stop and evaluate your own environment.
Oh, 100%.
So for you listening to this right now, take a look around your workspace or even think about the software tools you use every single day. Are you setting up your workflow based on how aesthetic it looks?
Like the perfectly color-coordinated calendar.
Right, the minimalist desk setup that looks so great on a video call? Or are you actually designing your environment with three-way pipes?
Are you building ugly, highly functional structures that actually trigger your brain into its deepest state of focus?
Because we routinely trap ourselves in these high-friction environments simply because they photograph well or, because they feel sophisticated.
Yeah, we choose the terracotta pot over the PVC pipe.
Exactly. But here's where this synthesis gets really profound. We've established that a fish tank and a seedling tray are just environments we optimize by managing variables and triggers.
Right.
So what happens when we take these exact same biological principles and apply them to complex digital systems?
Well, we pivot straight into the architecture of software and networking. And honestly, the operational overlap is just striking.
This is where we dive into things like Haskell programming, managing CI/CD, which, by the way, stands for continuous integration and continuous deployment, and the really highly complex routing of Wi-Fi 7 network traffic.
Right. Huge, abstract digital concepts.
But nestled right alongside these dense technical concepts in our sources is a very specific biological problem.
Managing an aggressive, dominant aquarium fish called the golden mabuna.
Right. And as I was looking at these two concepts side by side, a massive realization hit me.
Okay, what was it?
Managing an aggressive golden mabuna in a community fish tank is exactly the same mechanism as handling an unruly piece of state in a functional programming language like Haskell.
Oh, I love that connection. Let's really pull that apart because the architecture of that analogy is just flawless.
So think about it. If you have a golden mabuna and you don't physically isolate it or at least break up its lines of sight, it just wrecks the whole system.
Right, because it's incredibly territorial, it attacks the other fish, it hogs all the food resources.
Yeah, it creates utter, unpredictable chaos in your beautifully balanced tank. Now, in software engineering, state refers to the stored information a program has at any given moment.
Like a user's logged in status or the item sitting in a shopping cart.
Exactly. And if you have what programmers call mutable state meaning data that can be changed by any part of the program at any time, it acts exactly like that aggressive fish.
It unpredictably alters other parts of your code.
Yes, it creates massive cascading bugs that are just nearly impossible to track down.
Because the digital environment lacks strict boundaries. In traditional imperative programming, it's like having all your fish swimming in one giant open bowl.
Right. If one component modifies a piece of data, the ripple effects are felt literally everywhere.
But functional programming languages, like Haskell, they approach this entirely differently. They enforce strict environmental control using what are called pure functions.
And a pure function is essentially the digital equivalent of our smooth, easily cleanable three-way plastic pipe, isn't it?
Functionally, yes, absolutely. A pure function is a piece of code that operates in total isolation. If you give it the exact same input, it will always produce the exact same output.
Okay.
And critically, it produces zero side effects. It doesn't reach outside of its own little boundary to mess with global variables or alter the rest of the application. It is entirely predictable and sterile.
So it doesn't trap hidden errors, just like the smooth PVC pipe doesn't trap toxic ammonia.
Exactly. Now contrast that pure function with a messy, interconnected piece of legacy code where every variable kind of touches everything else.
Right, that legacy code is your porous, algae-covered terracotta pot.
Yes. When a bug gets trapped in there, it is embedded deep in the microscopic architecture, and you have to tear the entire multi-million-dollar system apart just to clean it.
Wow, that makes so much sense. But Haskell also utilizes structural triggers, right? Like guards and pattern matching.
Yeah, so guards are literal logical boundaries written into the code that check specific conditions before letting data pass through.
Which is the exact digital parallel to using rocks or PVC pipes to physically break up the lines of sight in an aquarium.
Exactly. So the golden mabuna literally cannot see the other fish to attack them. You are aggressively managing the traffic.
But wait, even with pure functions and guards, a software program still has to interact with the messy outside world at some point, right?
Yeah, it has to.
It has to talk to databases, take user inputs, print things to a screen. How does Haskell handle that chaotic, unpredictable data without contaminating all the pure functions?
This is where we introduce the concept of a monad.
Okay, I have to admit, monads have always sounded like impenetrable math jargon to me.
Yeah.
How do they actually fit into this whole environmental design idea?
So think of a monad like a hazmat suit for your code.
Yeah, hazmat suit. Okay.
Yeah, you have this messy, unpredictable, toxic operation like fetching data from a server that might randomly crash.
Right, you can't control the server.
Exactly. So instead of letting that chaotic operation touch the rest of your clean, pure system, you wrap it inside a monad.
Oh, I see.
The monad is just a container. The program can still carry this operation around. It can pass it from function to function and utilize its contents. But the chaos is entirely contained inside the suit.
The toxic side effects basically can't leak out into the global environment.
Exactly.
That is just a brilliant mechanism. You aren't getting rid of the dangerous element. You are just encapsulating it.
Right.
Which transitions us perfectly into the networking side of things, specifically analyzing Wi-Fi 7 MediaTek traffic. Because it's really all about directing the flow of invisible chaos.
It really is.
But exploring this raises a really fundamental question. Is the ultimate goal of any complex system, whether we are talking about routing wireless data packets, writing an enterprise Haskell application, or maintaining a Cichlid tank, is the goal to completely eliminate chaos or just to contain it?
Well, that is the dividing line between theory and reality. You cannot eliminate chaos.
Right.
A living system, by the very laws of thermodynamics, generates entropy. Fish produce toxic waste. Garden pests arrive. Human users input terrible, badly formatted data into your software.
And wireless networks experience massive interference from like microwaves in your neighbor's routers.
Exactly. The goal of a master architect is never to create a sterile, completely dead environment where nothing unexpected happens. The goal is to design containment protocols.
So let's look at how Wi-Fi 7 actually achieves this containment.
Mm-hmm.
Older generations of Wi-Fi handled interference essentially by just trying to shout louder over a single frequency.
Which led to massive bottlenecks.
Right. But Wi-Fi 7 introduces a really cool mechanism called multi-link operation, or MLO.
An MLO is a phenomenal example of dynamic containment. So older Wi-Fi is like a delivery truck stuck on a single congested highway. If there's a traffic jam, the data just has to sit there and wait.
But Wi-Fi 7 with MLO gives that delivery truck the ability to drive on 3 different highways simultaneously.
Right, the 2.4 gigahertz, the 5 gigahertz, and the 6 gigahertz bands.
So it can instantly split the data packets across whichever lane is clear at the exact millisecond it needs to transmit.
Yes. It doesn't eliminate the traffic jam, it just dynamically routes the water around the rock.
It manages the dominant variables. You use the MLO to bypass network interference. You use monads in Haskell to wrap volatile database calls in a hazmat suit.
And you use the ugly three-way pipes to gather organic waste where it can be siphoned out in 5 seconds.
System optimization isn't about achieving perfection at all. It is about managing inevitable chaos gracefully.
Absolutely.
Which brings us to the final and honestly perhaps the most vital layer of this entire deep dive.
Yeah, this is the really critical part.
We have spent a lot of time today analyzing the visible structural interventions. So the plastic pipes, the placement of the grow lights, the pure functions, the Wi-Fi band.
Right, the things you can point to and see working.
But every single system we have discussed relies on a foundation that is entirely invisible to the casual observer.
The unseen engine.
Yeah. In the fishkeeping world, this is called the substrate. The deep dive materials note that the arrangement and the specific material of the substrate is a critical ongoing point of study.
Right.
But to a beginner, just looking at an aquarium, the substrate just looks like decorative gravel. It's just there to cover the bare glass at the bottom of the tank. Why is it actually the most important piece of the entire puzzle?
Because the substrate, that deep layer of sand or porous gravel at the very bottom of the tank, is the ultimate breeding ground for the microscopic beneficial bacteria.
Okay, so it's not just rocks.
No, not at all. You can install the most highly optimized three-way pipes. You can perfectly simulate a barometric monsoon drop. You can have the most elegant, pure functions in your code. But without that massive, invisible colony of bacteria living in the substrate, the biological engine stalls completely. The bacteria are what actually consume the toxic ammonia and convert it into harmless nitrate.
Wow. So without them, the environment just becomes lethal in a matter of days.
Literally. It is the silent workhorse of the environment. The substrate is doing like 90% of the actual heavy lifting of keeping the system alive, completely out of sight.
So every system basically has a substrate.
Every single one. It represents the foundational infrastructure that enables the high-level applications to even function.
Right. So in a garden, it's not the dude itself, but the microscopic fungal networks and the microbial life in the soil that actually break down the nutrients so the plant's roots can absorb them.
Exactly. And in software engineering, the substrate is the bare metal hardware, the operating system, or just the fundamental data structures. You can write the most beautiful user interface in the world, but if your underlying database architecture is corrupt, the whole application crashes.
So let's translate this directly to you, the listener. We talked a lot about digital architecture and biology, but what is the substrate in your own operational life?
Well, that requires a very honest audit of how you actually function day to day.
It really does.
Yeah.
Because it is incredibly easy to get caught up in optimizing the visible high-level structures, isn't it?
Oh, yeah. We buy the $40 productivity planner. We download the newest AI task manager.
Right. We arrange our physical desks to look like a sleek Silicon Valley startup. We are constantly putting beautiful terracotta caves in our tanks.
But what is your cognitive and operational substrate?
Exactly. The underlying systems that actually process the load. I'm not just talking about the basic stuff like getting enough sleep or drinking water. I'm talking about your baseline information architecture.
How is your computer's hard drive actually organized?
Yes. What is your baseline routine for processing your email inbox so it doesn't become this toxic reservoir of anxiety? How do you manage your cognitive load before you try to execute a massive creative project?
Those foundational tools are really rarely exciting.
They aren't aesthetic at all, but they are the operational substrate that filters out the friction of daily work.
Right. Because if your file management is a disaster or your baseline communication habits are just chaotic, I don't care how optimized your new calendar app
The
is.
system is just going to crash under the weight of its own entropy.
Optimization fundamentally fails when the foundation is ignored. Whether you are routing packets on a MediaTek network, writing an application in Haskell, or just trying to propagate a delicate plant cutting.
If the underlying environment isn't structurally sound, all your high-level interventions are basically just decorative band-aids.
Exactly.
So let's pull all of these threads together. We started today by looking at a cheap, honestly incredibly ugly plastic three-way pipe used for breeding cichlid fish.
Right.
And by tracing the logic of that single hyperfunctional choice through botany, through the pure functions of Haskell programming, and through the dynamic routing of Wi-Fi networks, we uncovered a pretty universal truth about system design.
We really did. True, resilient optimization requires a willingness to basically ignore pure aesthetics.
Yeah.
It demands a focus on cleanability, the establishment of strict structural triggers, and containment protocols to manage chaos. And above all, it requires an obsessive focus on building a strong, unseen foundation.
You have to be willing to be a little unglamorous and maybe a little unconventional if you want the system to actually thrive in the real world.
Yeah, absolutely.
Which brings us right back to that designer terracotta pot,
Yeah.
or that legacy software system. As you step back into your day, I want to leave you with a completely different way to look at all this.
Okay, what is it?
We've spent this whole time talking about eliminating friction and removing the porous traps in our environments, right? But consider this. If we successfully sanitize our physical, digital, and mental environments so completely that there is absolutely zero friction left, do we lose the very resistance required to grow?
Oh, that's a really interesting point.
Muscle only builds when it faces resistance. Plants only develop strong roots when they have to literally push through dense soil. Maybe the ultimate goal of system design isn't to build a completely frictionless life.
Maybe the goal is simply choosing exactly which friction you want to keep.
Exactly. Something to think about.